Hello there and welcome to Upper 6 Further Maths. Here we're looking at the sum of complex number series so we can answer questions from exercise 1e. Here we're looking at part 1, which is the finite summation type questions that we can expect in this section. So what we're going to do first of all is we're going to look back into A-level maths and into the geometric sequence and series chapter. That's chapter 3 of the A2 textbook. What we'll see is that when we have a geometric sequence like this sequence here, it starts at the value a and then we multiply by the term r each time. We use the letter r for a ratio between the terms of our geometric sequence up to a certain value ar to the power of n minus 1. We stop at ar to the n minus 1 because if you think about it, this is the first term, this is the second term, this is the third term, fourth term, fifth term, sixth term. So there is always one less multiple of r than the term we're currently at. So this is the nth term of this geometric sequence. If we were to add all of the numbers in this sequence up together, the addition of the first n terms is this formula here. A brackets r to the power of n minus 1 over r minus 1. And in the second of this video, if the ratio is smaller than 1, then we can add this up to infinity, and this would be the result. But in this video, we're just going to concentrate on the summation of finite sequences. So, let's see a question. We're given here that s is equal to e to the I theta plus e to the 2 theta I plus e to the 3 theta I, all the way up to e to the 8 theta I. This is what we're given in the question, that s is equal to this. And in this question, we're asked to show that s is equal to this very strange and very complicated looking expression here. Well, where on earth would you start for this? Well, the first place we'd start is we'd recognise that s is a geometric summation. You can see here that the ratio between the terms in this geometric sequence is e to the theta I. We're multiplying by an extra e to the theta I each time to increase the indice by 1 theta I each time. So in this expression, the first term in the summation is a, so we're going to set a equal to e to the theta I. The second term in the sequence is ar, where in this sequence it is e to the 2 theta I. If we know that a is equal to this thing here, we can rearrange that into the formula, or substitute it into the formula rather, and then cancel out e to the theta I on both sides. That would cancel out one of these theta i's on the other side, but not all of them. So we can clearly see here that the ratio is e to the theta I in this sequence. We're multiplying by e to the theta I as we go through the terms in our sequence that we're adding. And the number of terms we're adding here is 8 because we have 8 terms in our sequence, 1 theta, 2 theta, all the way up to 8 theta. So these are our variables. Then we have a, r, and n. Now we can substitute it into the geometric sequence formula. So let's substitute it in then, and we're off to a start here. It's now starting to look a little bit more similar to this expression we are summating to get. So e to the theta I is a, r to the power of n, that's e to the 8 theta I, minus 1 over r minus 1. There we are. Now the next thing we'll do is we'll just expand that numerator to get e to the 9 theta I minus e to the theta I. So that's difficult step number 1. Now difficult step number 2, for seemingly a random reason, but I'll show you the reason in a second, is we're going to multiply both the top and the bottom by e to the minus theta over 2 I. Let's do it and I'll show you why. So we'll do it first. That's going to be 18 theta over 2, and then times by e to the minus theta over 2, that's down to 17 over 2 theta I. In the second part here, we have e to the theta I times by e to the minus theta over 2i, so that's going to give us e to the theta over 2i. Remember, we add indices in this case, and we're adding a negative number here. On the denominator is the same as the numerator second term, and on the bottom it's just times by 1. Now, why have we done this? Well, if you look at the denominator, what we see is that the powers are equal, but one is positive and one is negative. Now, what this hopefully should remind you of is in the last video, we had this expression here, where z minus 1 over z is equal to 2i sine theta. Now, z here is representing cos theta plus I sine theta, or in fact, e to the theta I. Now, in this case, we can just set the theta value to be theta over 2, and that will simplify the denominator to 2i sine theta over 2. So that's why we've done this expression here, because the negative power will make it 1 over that value there, and it will simplify using that formula. So that's difficult part number 2. Difficult part number 3 now is to sort out the numerator. Now we can see here on the numerator, we'd ideally like to factorize out this term here at the start. So I'm going to factorize e to the 9 theta I over 2. And what will I get in the bracket here? Well, if I pull out 9 theta over 2, that's going to leave me with 8 theta over 2 on the first term. That's 4 theta I. And if I've got theta I over 2 here and factorize out this, that's going to leave me with minus 8 over 2 theta I, so that's minus 4 theta I. Now, what we've got again on the numerator here is another opportunity to use this second rule here. We've got e to the 4 theta I minus e to the minus 4 theta I, and that's exactly what we have on the left hand side here, so we'll simplify it using what we have on the right hand side there. Just now, theta is not just going to be theta, it's going to be 4 theta. What we can then do is cancel out the two i's on the top and the bottom, and there we are, voila, we have this S sequence or summation equal to this really difficult formula here. Let's just see it all again in the match of the day action replay. We had S equals this thing here. First thing we do is we recognize it's a geometric summation. Worked out that we have an A value of e to the theta I, an R value of e to the theta I, and an N value of 8. 8 terms we're summating here. We apply the summation formula for a geometric sequence. Then we expand the brackets. Then we sort out the denominator first by making sure that the powers on the denominator are equal by multiplying on the top and the bottom wherever we need to. Then this is the first opportunity to apply this sine rule here. So 2i sine theta over 2 appears on the bottom. Then use the question to give you a bit of a clue as to what to do next. You need to factorize out this expression here, e to the 9 theta I over 2. So do that and see what you get, and hopefully it'll be another opportunity to use this sine rule here. So then you can simplify that to 2i sine 4 theta, and then you get your answer by cancelling out 2 i's on the top and the bottom. So a little match of the day action replay there. You have to do all of that just for part A. Bringing in part B now. Let P equal cos theta plus cos 2 theta plus cos 3 theta all the way up to cos 8 theta, same for sine. Use your answer to part A to prove that P is equal to this expression here, and find a similar expression for Q. So what we're going to do is we're going to consider P plus QI, just strategically added together. What we'll do is we'll add the first two components of P and Q together, multiplying the Q component by I. Do the same for the two second components. Do the same for the two third components, and do the same all the way along until you've done the same for the last component. Always multiplying the I component by I, because Q is being multiplied by I. And what you'll see here is we'll have exactly the same thing as we have in the summation for S. This thing here, we're just changing it from argument modulus form to exponential form of the complex number. So this is equal to s. So we've now proved that p plus qi is equal to s. Well, how does this help us? Well, this helps us because out of s, that's this thing up here, if we just take the real part of it, that will give us an expression for p, and if we just take the imaginary part of it, that will give us an expression for q. So let's go ahead and do that then. Let's take the expression for s, rewrite out what this exponential complex number is going to be. It's going to be, so this is exponential form of the complex number, this is so this is modulus argument form of the complex number. And for p, we're just going to take the real part of it, so ignore the complex part of it, and we'll have cos 9 theta over 2 sine 4 theta cosec theta over 2. Cosec, because we have sine on the bottom here, we just moved it up to the top and called it cosec. And we can do exactly the same thing for q by just taking the imaginary part and ignoring the real part, and q will equal sine 9 theta over 2 sine 4 theta cosec theta over 2. So there we are, that's part B of this question done then. So these are the types of questions we're expected to do then. Quite long, quite complex questions that involve using the geometric series summation formula for complex numbers. So your turn to have a go at the only question in the textbook that is of this type. So pause the video and give this part A a go. Okay, so let's get started then. So let's write out what p plus qi actually is. So p plus qi equals, so let's add it together in a very strategic order. It's going to be 1 plus, now first of all I'll add these two terms together here, multiplying the q term by I. So that's going to give me cos theta plus I sine theta. I'll add together these two terms now, so that's going to be cos 2 theta plus I sine 2 theta. Remember, you always have to multiply the q part by I first before you add it on, and then we'll just jump all the way to the end. We could do it with the same as sine and cos of 3 theta, but we'll just jump straight to the end, and it's going to be cos 12 theta plus I sine 12 theta. Now what we should notice here is now we can convert this from argument modulus form into exponential form. So it's going to look like this thing here. So what we now need to notice, difficult part number 1, is that this is a geometric series summation. In the formula, A is represented by the first term, which is 1, R, which is representing the common ratio between the terms we are summating, which is e to the theta I, and n is the number of terms we're adding together, so there would be 13 terms in this sequence here, because we start with a 1, and then the second term is just theta I, the third term is 2 theta I, the fourth term is e to the 3 theta I, so it would be the 13th term that will be e to the 12 theta I. Now the series summation formula is a bracket r to the m minus 1 over r minus 1. So we'll use these three values to substitute in. So it's going to be 1 multiplied by e to the theta I to the power of 13. So let's multiply the two powers together there. And then minus 1. Divide by e to the theta I minus 1. Now let's expand the brackets first of all, but we'll also at the same time, difficult part number 2, need to notice that we need to times both top and bottom by e to the minus theta over 2i on top and bottom. Now that will end us up with, so it'd be 13 theta I, that'd be 26 over 2, take away a half, that's going to be e to the 25 theta over 2, minus e to the minus theta over 2i, and we'll divide then all of that by e to the theta I times that, that's e to the theta over 2i, minus e to the minus theta over 2I. Great, we're nearly there for finishing off part A. What we need to do now is sort out the denominator, and it suggests that we factorise out e to the 6 theta I. So that's 12 over 2, so I'll be left with 13I theta over 2. And this is a minus, so that's going to be factorising out 12 theta over 2 more, so that's going to be minus e to the minus 13 theta over 2I. And on the denominator, that will stay exactly the same. We've just done a bit of factorising on the denominator, on the numerator, sorry. So it's going to be e to the theta over 2I minus e to the minus theta over 2I. So there we are, we've done part A. Let's now move on to part B then. Pause the video and give this part a go. Okay, so moving on from part A, this is part B, just carries on straight away on from part A. If we consider P plus QI, and now what we're going to do is rearrange, so use the rule for the top and the bottom that Z minus 1 over Z equals 2I sine n theta. So n is on the powers here. So on the power of 13 over 2 theta, that's what goes into sine here. So it's going to be e to the 6 theta I, brackets 2I sine 13 theta over 2. And on the denominator, it's going to be 2I sine, and on the power of n here is going to be theta over 2. So Q here, so let's rewrite this out now. We'll rewrite this using the argument modulus form of e to the 6 theta I as a complex number. So that's going to be cos 6 theta plus I sine 6 theta. And then we'll rewrite out the rest of it. Actually, we could cancel out 2I on the top and the bottom, so it would be sine 13 theta over 2. And actually, we could rewrite sine theta over 2 as cosec theta over 2. Now, the next thing we'll do is for Q, it would just be the imaginary part of P plus QI. And that will ignore the real part, so it's going to be sine 6 theta, sine 13 theta over 2, and then cosec theta over 2. And for P, that's going to be the real part of P plus QI. So that's going to be the cos part of it. So cos 6 theta. We'll ignore the imaginary bit and then we'll just expand these last two terms. So that would be sine 13 theta over 2 and cosec theta over 2. So there we are. That's an expression for Q and a similar expression for P. And let's move on to part C of this question then. Pause the video and give this part a go. Okay, so if we want P plus QI to be real, then Q has to equal 0. It has to have no imaginary part to it. So if we want sine 6 theta sine 13 theta over 2 or cosec theta over 2 to equal 0, then one of these components has to equal 0. First of all, this component here is never 0, so that's automatically out of the game. So it's either sine 6 theta that equals 0, or it could equal pi because, so yeah, it could equal 0. So therefore 6 theta, now what function of sine will give us 0? Well, either sine of 0 will give us 0, sine of pi will give us 0, sine of 2 pi will give us 0, sine of 3 pi will give us 0, sine of 4 pi will give us 0, sine of 5 pi will give us 0, and sine 6 pi will give us 0, but that will go out of the range eventually. Now if I divide through by 6, I'm going to get 0, but that's not in the range, so I'll scrap that solution. Divide through by 6 on this solution, that would be pi by 6. Divide by 6 on this solution, that would be pi by 3. Divide by 6 on this solution, that would be pi by 2. Divide by 6 on this solution, that would be 2 pi by 3. And divide by 6 on this solution, that would be 5 pi by 6. Let's do exactly the same thing for sine 13 theta over 2 equals 0. Therefore, 13 theta over 2 will either equal 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, or 6 pi. And by the time we've gone past there, it will be too high. Now actually 0 is out of the range, so we won't include that. So what we'll do is we'll times by 2 and divide by 13. So theta is either equal to 2 pi by 13, 4 pi by 13, 6 pi by 13, 8 pi by 13, 10 pi by 13, or 12 pi by 13. And if you go any further, you'll be at 14 pi by 13, which is outside of the range for theta. So there we are. We have a ton of solutions here to when p plus qi is real. And there we are. That's the answer to this question then. Now, hopefully what I've done by the time the video is published is I'll have put in the description of the video a Google document link to a bunch more questions similar to this, but slightly different to this. So very similar in terms of it will be a summation, a finite summation of complex numbers, ones for you to practice on so that you get better and better and more fluent at these types of questions. Okay, so move on to part 2 to complete exercise 1E, but otherwise thanks very much for watching.